Okay, this is video 2 on expected value. We are looking at this theorem. So for a uniform probability space, the expected value of a random variable is the average of the random variable's value on each outcome. The theorem itself tells you that this should be the case, but mathematically we should be able to prove it maybe from an experiment. So that's what exactly we're going to do here. So the expectation of x, what this is stating, this is the statement um, in mathematical terms is that the expected value of x, let's say this is in a uniform probability space, is essentially the cardinality of my sample space and just the sum of all the x's such that x belongs to my random variable x that's defined on a sample space S, right? So let's consider this example of rolling a pair of dice because we know that this has a uniform probability space, right? So pair of dice and it's fair, so it's not biased at all, right? Now, if you think about the random variable we are interested in, let's say x is the sum that appears on both, right? So I'm interested in that sum. So sum that appears based on like what value appears on each of the dice, right? Okay, so thinking about the probability space first, because we will require going back, like we are plugging in the values in this formula, right? So I need this x and I need this px of x, right? So let's first focus on what is px of x. For every outcome, this is going to be 1 over 36. This is known why? Because we are considering fair dice and every possible pair is equally likely. There are 36 such pairs, and so the probability of just one of them is going to be 1 over 36, right? So this is known. Now let's try finding out what values does x take, right? Because x is the sum that appears on both dice. We can actually visualize this problem. So let's say this is my die 1 and let's say this is my die 2 and these are the values that appear, right? That can appear. So 5 and 6, 1, 2, 3, 4, 5 and 6. So here I'm going to write the sum of the values. So if 1 and 1 show up, I get 2. If 1 and 2 show up, I get 3, 4, 5, 6 and 7. Similarly here I can get 3, 4, 5, 6, 7, 8 and so on, right? So I can fill up this entire table, so to say, right? And now I'm interested in x, right? The way to get x is simply pick up a value from here, right? So essentially I'll be picking up all of these 36 values, right? And then I already know that the probability of each of these values occurring is 1 over 36, right? So if I plug in those values in my formula for the expectation for x from the previous slide, I know that this is going to be 1 over 36 times 2, or maybe like even like making it more concise, I can say sum of column 1, right? Because each one of COLUMN 1, right? Which is this column. And then again plus 1 over 36 times sum of column 2 and so on, right? So if I simplify this, I can see that all I'm doing is I'm getting the sum of all the values of all the possible values, and there are 36 of them, obviously 6 times 6, right, over 36, right, which is nothing but, and maybe I'll write it here, which is nothing but 1 over the cardinality of the sample space, which is like 36 of them, and then summing up the actual x's over all possible values of x, right? So this actually reduces to something more simple here. And this is pretty evident from the definition of expectation itself. So this is what the theorem stated here. Okay, let's look at the same problem from the point of view of a probability distribution function, because we are essentially trying to equate that the expected value from the probability distribution function and the expectation from the probability space, which we just calculated, are actually the same thing, right? So let's again consider the PDF of the sum of two dice, right? So I can like write that down here quickly. All possible values of x. So the all possible values of x are 2 up to 12, right? So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, right? And then there is this associated px of x for each of these, right? So the probability for 2 just appeared. We can just like go back and write this all by ourselves. So 2 just appears once, right? So the probability of that is 1 over 36. 3 appears 2 times, so this is going to be 2 over 36, which is 1 over 18. 4, I think, appears 3 times, so this is going to be 3 over 36, which is 1 over 12. And then again 5 appears uh, 4 times, I think, so 9 fours are 36, so 1 over 9. So similarly we can calculate the entire PDF for this experiment, right? So 5 over 36, 1 over 9, 1 over 12, 1 over 18, and 1 over 36, right? Now the expectation or the expected value for this random variable x, the sum that shows up is by definition x px of x, which is what we defined initially, right? So all I have to do is multiply like each of these x's by their probability uh, value, right? So, oops, I don't know, here, yeah. So all I have to do is like keep multiplying these. For example, this will be 2 over 36 plus 3 over 18 plus 4 over 12 and so on, right? Idea being the same that we saw earlier when we were calculating these from the actual probability space, right? Because we have summarized the probability space in terms of the probability distribution function, right? So this is another theorem that I'm not formally stating anywhere, but this is a theorem that the expectation from the probability space and the PDF are always equal, right? So let me state that mathematically. If x is in S, and I am finding like the individual x's and the individual probability for each of these x's, that's essentially the same thing as finding all the x's in the sample space and then multiplying them by their probabilities in the probability distribution function, right? Or by their PDFs. Okay, so this finishes this video. In the next video, I'll talk about expectations for different distributions.